Welcome, my dear students. In this part of the video, we are going to discuss some important concepts of the lesson, that is chemical kinetics of a CBSE class 12. So to begin with, I am doing a quite very important 3-mark question, which is important for the board examination, that is derivation of integrated rate equation for zero order reaction. Derivation of integrated rate equation for zero order reaction. So you know, order means sum of powers of concentration term in an experimentally determined rate equation or a rate law. So if that order is 0, then it is supposed to be called a zero order reaction. If it is order is 1, then it is called it as a first order reaction. This derivation is quite important for 3-mark in the board examination. Almost very important question of 3-mark. They will directly ask you to derive the integrated rate equation for zero order reaction. So let us consider what is zero order reaction. We say zero order reaction means the rate of a reaction is proportional to zero power of, see this, zero power of concentration term, of reactant. So this is a classic definition of zero order reaction. So we'll begin with the derivation. For that we consider zero order reaction, that is R giving P. Reactant gives product. So for this one, if I write rate is equal to, that I write an instantaneous equation minus dr upon dt. Concentration decreases with respect to reactant, that's why here negative sign will come, and that of product, positive sign will come. That is what instantaneous rate and average rate. And similarly I can write a rate is equal to rate constant into concentration of reactant raised to how much you tell, 0, because power of concentration term is 0. That is what the rate of reaction is supposed to be called. So let us call this as equation number 2. See, for equation number 1 and 2, I think left side they are same. Therefore what I will do, I will equate this. If I equate, what I get then? Equating equation number 1 and 2. See here, very carefully you observe. I am equating equation number 1 and 2. So what is there on the left side? Rate. In equation number 2 also there is a rate. Therefore I can write minus dr upon dt is equal to k into r raised to 0. So very simple. If I equate these two, I get this equation. Or rearranging, I can write minus dr upon dt is equal to k, because r raised to 0 becomes 1. Transferring dt this side, I will bring them into this side and write. That becomes minus dr is equal to k dt. Correct? I am transferred the dt that side, it becomes dt. Now negative sign I will transfer that side, that becomes a dr is equal to minus k dt. This is your equation number 3. To integrate it on both the side. So therefore I will do integration on both the side for equation number 3. So I get integration of dr is equal to minus k outside, it is a constant, it cannot be integrated, and dt. So you already know in the mathematics of integration part you might have studied the integration of dx is a x, like that I can integration of dr becomes r is equal to minus k outside. What is integration of dt is again as usual t plus I add integration constant, that is I. This is your equation number 4. After integration of equation number 3 we get that equation number 4. Then what I do, imagine the reaction is not yet started at time t is equal to 0 at beginning, in the beginning of the reaction where time is 0 seconds. If t is equal to 0, then the concentration of reactant will become R naught, that the final concentration will be equal to initial concentration. So these values I will substitute in equation number 4. Therefore I write substituting above value in equation 4, we get, you tell me what we get actually then. Instead of R, what I have to take? I should take it as R naught minus K into time 0 seconds you have taken plus I. So simplification of this becomes R naught is equal to I. So I will call this as equation number 5. Now we have got the value for equation number 5, that is integration constant. Now I will substitute value of I in equation number 4. I write substituting value of I in equation number 4, we get. So what we get then? There is already R is equal to minus KT plus instead of I should take R naught. So what I do is R naught I will transfer that side, that becomes R minus R naught is equal to minus KT. Correct? R minus R naught is equal to minus KT. What I do then, I want KT is equal to what? See KT. So KT is equal to, that becomes R naught minus R. Correct? R naught minus R. Then final I am writing K is equal to, that is your initial concentration R naught minus R divided by what will come? That comes as T. This is your final 6th equation. At this point I think the derivation is over. So this equation number 6 represents, that is the integrated rate equation for 0 order reaction. But look into this equation. This equation is in the form of y is equal to mx plus c. Compare and tell. So on the y-axis, if I plot a graph, students, if I plot a graph, on y-axis what I have to take? I have to take r. Then on x-axis what I have to take? T. Then I get a straight line with a negative slope, like this. And it intercepts on this y-axis. This point we call it as r naught, that is y-intercept. And if I take a slope for this line, then that slope will be equal to minus k. So this is the derivation for the integrated rate equation for a 0 order reaction. So up to this point, I think there is no difficulty at all. So thank you for watching the video. In the next part of the video, we are going to derive the integrated rate equation for first order reaction. Thank you for watching the video. If you have not subscribed to the channel, please subscribe it, like the video and share the video. Thank you everyone.